Let us now take an example and see how to design an inductor. Consider a buck converter. We have discussed and studied the buck converter at some length. We know how it operates. This is V0. Let's say V0 we want is 3.3 volts and I0 is 5 amp load requirement. The switching frequency is 20 kilohertz, 20,000 hertz. VI input voltage 10 volts plus or minus 10%, varies from 10 volts minus 10% to 10 volt plus 10%. This is Q, D, L, C and R0. And our job is to design L inductor. So let us try to find the duty cycle. Vi max into D min is equal to Vi min into D max should be equal to V0. Buck converter relationship. Now Vi max 10 volts plus 10%. 10% of 10 volt is 1 volt. So 11 volts into D min or 9 volts into D max is equal to 3.3 volts. D min, from that relationship, D min will turn out to be 0.3. D max is 1.1 by 3. We will need the D min value. L is equal to V0 into 1 minus D min divided by delta IL into Fs. While we discussed the buck converter, we had used this equation. We had developed this equation. L is equal to V0 into 1 minus D by delta IL into Fs. I am now including it as D min because D min is worst case when D is minimum. This value in the numerator within the brackets is maximum and I will get the largest value of L. So that would be the worst case. So let us plug in these values. Is 10% of 5 amps, which is 0.5 amps. Fs is 20 kilohertz. This is 3.3 volts, 0.3, and you will land up with L 0.23 millihenry. So this is the value of L. That is the first step in the design of the inductor. Find the value of L, which we have done from the understanding of how the buck converter operates. Next, let us try to find the area product. So for finding the area product, we need these values. What is Im? Because in the energy equation, we have EL is equal to half L Im square. What is Im? Im is, you know that the current in the inductor, the average value is I0 and there is superimposed on that delta I ripple peak to peak. So the peak value will be Im plus delta IL by 2. This we know, we have studied 5 plus 0.25, 5.25 amps. Then the energy in the inductor at peak current will be half LIM square, which will turn out to be 3.1834 into 10 to the power of minus 3 joules. And now the area product can be calculated 2EL divided by KW, KC, JBM. We know all the values here. I am going to take KW as 0.6. An experienced winder will wind this. KC is the crest factor, which is Im by I0. I0 is the RMS value. You can find that out. J is 3 into 10 to the power of 6 ampere meter square. Bm is 0.25 Tesla for ferrites. We are using ferrites. And this will work out to be 1.34747 into 10 to the power of minus 8 meter to the power of 4. Or it works out to be 1 multiplied by 10 to the power of 12. You will get 13474.7 mm to the power of 4. Now look into the core table and try to select a core which will give a value greater than this. Now let us look at the core table. Now here is the core table. I am now looking at the area product column. This is the area product column. Then look at this 1347, 13,474. You are having 10,200, P30, 30 bar 19. Greater than that, 20 20,301. Now this is greater than the one that we have calculated, so it is good to choose P36 bar 22 pot core. Of course, you can choose any other core shapes, but let us say for now, for example, we choose this pot core. So select pot core P36 bar 22. So this is the core that we have selected. Now what are the values for this core, the selected core? We have the core cross-section area of 201 mm square. We have the window area of 101 mm square. And we have the mean magnetic length of 53.2. So let us write that down here. Core cross-section area of 201 mm square, window area of 101 mm square, total area product, which is the multiplication of this, is 20100 mm to the power of 4, and Lm, that is the mean magnetic length, 53.2 mm. So these are the parameters for the selected core, which is the pot core P36 bar 22. Next, let us calculate the permeance. See, from the data sheet of CeLHP3C grade ferrite, I have obtained the value of relative permeability as 2000 plus or minus 25%, where the worst case permeability minimum value is 2000 minus 25%, 1500. So I will use this permeability, minimum permeability for the calculations in evaluating permeance. So in the permeance, if you look at the permeance equation, mu naught mu r AC by Lm plus mu r Lg, this is what we had developed. We know AC, we know mu r, we know mu naught, we know Lm, mu r, Lg, the air gap. You pick up a piece of paper or a mylar sheet, measure the thickness of that, and then you can plug that in here. For now, I'm going to take a paper of thickness 0.5 mm. So plug in the values. Let's say mu naught is 4.10 to the power of minus 7. Mu r is 1500 as given here. AC is 201 10 to the power of minus 6 meters square. Lm is 53.2 10 to the power of minus 3 meters. Mu r is 1500 again, and Lg is 0.5 mm. So 0.5 10 to the power minus 3 meters. So this will work out to 4.717 to 10 to the power of minus 7 Henry per turn square. So this is the value of the permeance. So once we have obtained the permeance, next it is easy for us to obtain the turns, number of turns that are needed to be wound on the inductor core. This is given by the relation N is equal to root of L by permeance, square root of that. So this is 23.13. Choose, round it off to the next upper integer, 23 turns, and this is N. Next, we have to find the wire gauge. The area of cross section of the wire be calculated, IRMS by J, which is I naught by J, this case, which is 5 amps by 3 into 10 power 6, which turns out 1.67 10 to the power of minus 6 meters square, or 1.67 mm square. Now look into the wire table. So look into the wire table. We need to look at a wire bare conductor area having greater than 1.67 mm square. Let us go down this, and you see that here SWG16. Now here in this row you will find SWG16, which has bare conductor area of 2.075 mm square greater than this. So pick that value. So now let us write down, select SWG16, which has a wire cross section area of 2.075 mm square. SWG16 is selected, and this has to be wound onto the inductor core, which we have chosen P36/22. There is a last check that we need to do, what is known as the window area check, to see if the windings will fit into the available window area. AWKW is 101 mm square into 0.6, which is 60.60, and N into AW, that is wire cross section, as we have read out from the wire table, is 23 into 2.075, which is 47.75. And you see that AWKW is greater than N into AW, and therefore the inequality is satisfied, and you know that this number of turns of this gauge will fit into the available window area, and therefore the design is successfully completed.